Okay, so our next lesson, we're going into section 8.4, which is going to be factoring and solving some polynomials. Specifically, we're going to focus on quadratic polynomials. However, I do want to first go over how to factor out a GCF. So if you remember back to finding a greatest common factor between, let's just say, two numbers. So let's say you have the number 6 and then you have the number 12. You want to figure out, well, what's the largest number that I can divide both of these by evenly? So let's say, for example, 6, all the factors of 6 are 1 and 6 and 2 and 3. And to get 12, you could do 1 times 12, 2 times 6, 3 times 4. So the largest number that goes into both 6 and 12 evenly, or as a factor of 6 and 12, would be 6. So that would be your greatest common factor. We can see that 3 and 2 are also common factors, but 6 would be the greatest one. So notice that the greatest common factor can never be bigger than the smaller of the two numbers that we're looking at. So you really just need to figure out what the factors are of the smaller value and then see which ones will go into the larger value evenly. So if I'm looking at number 1, for example, I have a 5 and a 20. So I know my GCF cannot be any bigger than a 5 since that's the bigger, or that's the smaller number here. And the only thing that I can divide 5 by is 5, aside from 1. So does 5 go into 20? Well, it does. So I know that my GCF is 5. So then what we want to do there is divide out that 5 from each of those terms. And that 5 is going to go on the outside of the parentheses. And what we get when we do the division, we put on the inside of the parentheses. So essentially, it's like we're undistributing in a way. So 5x divided by 5, well, 5 divided by 5 is 1, so it would be 1x, and 20 divided by 5 is 4. Now, if you needed to check your answer, you just distribute, which is what we had just finished doing in the last lesson. So if you were to do 5 times x, you would get 5x, and if you were to do 5 times 4, you would get 20, and that would put you back to where you started. So let's take a look at number 2. This time we have a 6 and a 3. So if I'm going to find my GCF, I know that it can't be any bigger than the 3 since that's the smaller of the two numbers. Well, does 6 divide by 3? It does, so we know that that's our GCF. So we're going to divide both of these by 3. Then what we get when we do the division, we're going to put inside these parentheses, and the GCF is going to go out in the front. So 6x divided by 3, well, 6 divided by 3 is 2, but we still have that x there, so it's 2x. And then 3 divided by 3 is 1, so it'll be minus 1. Now if we go to the next example, this time I'm going to look at my 7 and my 11. Now I know that there's no number that divides by both of those, so far my GCF is just a 1. But I do have a variable on both of these terms, and the variable on both of them has to do with an x. So on the first one here, I have an x squared. On the second one, I have just an x. Now, just like when we're finding the GCF of two numbers, it can't be bigger than the smaller of the two numbers. Same thing here with variables. So if you have an x squared, that's bigger or larger than just one x. So your GCF can't be bigger than the x. So as long as the variables are the same, it's just the smallest version of that variable, which in this case would just be x. So we're going to divide both of these by x, or 1x. We're going to put that GCF on the outside of the parentheses, and then whatever's left is inside. Now 7 divided by 1 essentially is still 7, but when you divide x squared by x, remember you're subtracting those exponents. So x squared divided by x is going to leave you with another single x. Negative 11, and then here x divided by x is just going to cancel out, so you're just left with that negative 11. Okay, now if we look at the next term here, I have a 4 and a 36. So my GCF here can't be bigger than a 4 since that's the smaller of the two numbers. And 36 does divide evenly by 4, so I know that's going to be at least part of my GCF. Then I want to look at the two variables. I have x, some version of an x on both, so I can take out a variable GCF as well. X cubed and just x, well, x is the smaller of the two, so that is part of my GCF as well. So now the 4x goes in front of the parentheses, and now I'm going to divide each of these. Now 4 divided by 4 is 1, right? So if you want to put the 1 there, you can. X cubed divided by x, remember this is really just x to the first power. You're subtracting those exponents, this will give you x squared. Then over here, 36 divided by 4 is 9, and x divided by x just cancels because 1 minus 1 is 0, and this is what you would left. This is what you would be left with. Now this 1 here is implied, so you can just erase that. You don't need to keep that on part of your answer. Okay, so moving on. So here I have a 24 and an 18. I'm going to look at those numbers first. So again, when you're going to find your GCF, remember it can't be bigger than the smaller of those two numbers. So 18 is the bigger value or the smaller value here, so we know the GCF can't be bigger than 18. So 18 does not go into 24 evenly. So let's think of some other numbers that do go into 18 evenly. So half of 18 is 9. Does 9 go into 24 evenly? It does not. What about 6 or 3? Well, 6 does go into 24 evenly. So does 3, but 6 is the larger one or the greater common factor. Now that takes care of the number portion here of these terms, but they both have some type of an x there. So the first term has an x cubed, the second term has an x squared. So remember, the smaller of the two is what gets to be part of that GCF. So my 6x squared is my GCF, and then now I'm going to divide that out from each term, and what's left goes in the parentheses. So 24 divided by 6 is 4. X cubed divided by x squared, if I subtract those exponents, I'm left with just a single x, or an x to the first power. Then here, 18 divided by 6 is 3, and x squared divided by x squared cancels out. So now let's take a look at the next one. So here, looking at the numbers first to determine my GCF, I have a -3 and a 21. Well, we know that the GCF can't be bigger than a 3 since that's the smaller of the two numbers. And 21 is divisible by 3, so we know we can take out a 3. Now, one added thing I'm going to put in here is that anytime the lead coefficient, so that's the coefficient of the variable with the largest exponent, is a negative, you want to take that out on your GCF as well. If another term in your expression is negative, that's fine. You just don't want your lead term to be negative. So we're going to take out a -3. Now, looking at the variables here, they both have some version of a w. There's a w to the 4th power and a w to the 3rd. So remember that the smaller one is the one that gets to be part of that GCF. So that would be w to the 3rd power here. So -3 w to the 3rd. Now -3 divided by -3 is just 1. So I can put the 1 if I want, but I don't need to worry about that. W to the 4th divided by w to the 3rd. I'm subtracting those exponents, getting w to the 1st power. 21 divided by -3 is -7, and then these w's cancel because they're the same. Okay, so now this next problem, I have a 2, a 10, and a 12, and these are all divisible by 2. So I know that my GCF here is going to start out with a 2. Then I have a y term, or a y is part of all of those terms. A y to the 3rd, a y to the 2nd, and a y, and the smallest one would be that y, so I know that that's part of my GCF as well. So I'm going to take my 2y and divide that out from all three terms. 2 divided by 2 is just 1, and y cubed divided by a single y, when I subtract those exponents, I get y squared. -10 divided by 2 is -5, and y squared divided by y, I'm going to subtract those exponents, and I'm just left with that 5y. And then at the end, these y's cancel, and negative 12 divided by 2 is negative 6. All right, now the next problem, I have a 5, a 30, and a 42. Now remember, the GCF cannot be bigger than the smallest number, and the smallest number is 5. Now the only thing we can divide 5 by is 5. Now 5 does go into 30. 30 can divide by 5 evenly, but 42 cannot, which means the only numerical GCF we have here is a 1, because everything is divisible by 1. Now we look at the variables. There's an x squared here. There's an x on the middle term, but there's no x value on that third term. So the only GCF here is 1, which means this is not factorable, because if you divide a 1 out of everything, nothing is going to change. You're still going to end up with the same expression. Okay, number 9, we have a negative 7, a 28, and a 21. Now, these three, the GCF can be no bigger than the smallest of those three, which is 7. 28 and 21 are both divisible by 7, so I know 7 is going to be part of my GCF. Now remember what I said to you in the other problem. Since my lead coefficient here is negative 7, I'm going to also put a negative on that GCF as well. Now we're looking at the terms. They all have the same variable in their terms, so m to the third, m to the second, and m. The smallest of those is just that single m. So our GCF here is negative 7m. And then when we divide that on each of these, so negative 7 divided by negative 7 cancels out to a positive 1. M to the third divided by m leaves me with m squared. 28 divided by negative 7 is negative 4, and the m squared divided by the m leaves me with just an m, or m to the first. And then 21 divided by 7 is 3, and they're both negative, so that's why it's a positive 3, and these two m's here canceled out. Okay, this one here, we have a 2, and a 60. So we know that the GCF cannot be larger than that 2, which is okay because 60 is divisible by 2. They also all have some version of the variable d, the smallest of them being d squared. So 2d squared is my GCF. So that goes out front. And now I'm going to divide each of these by 2d squared. So 2 divided by 2 is just 1. And then d to the fourth divided by d squared, I subtract those exponents, and I'm going to get d squared. If you want to put that 1 in front, then you can. Then here, 2 divided by 2 again equals 1. D to the third divided by d squared. You subtract those exponents, and you just get a d, or d to the first power. And then here, 60 divided by 2 is 30. And the d squares cancel because they're the same, and they would just equal d to the 0, which is 1. Okay, now the next one here, I have a 4 and a 144. So my GCF there, remember, can be no bigger than the smaller of the numbers, which is 4. And 144 is divisible by 4, so that works. Then we look at our variables. They have the same variables, both some version of a t. The smaller of the two is also part of my GCF. So I know my GCF here is 4t. So 4 divided by 4 is 1. And then t to the third divided by t, I subtract my exponents, I get t squared. So it would be 1t squared. Then 144 divided by 4 is 36, and those t's are going to cancel. Okay, now number 12, my GCF here, remember, GCFs can never be bigger than the smaller of the two numbers, so 3 is the smaller number here. 12 is divisible by 3, so that's good. However, my lead coefficient here, this 12, is a negative, so I want to take the negative out on the GCF as well. Now I look at the variables. I have variables on both, but they're different variables. One is a t and one is a z, so I can't take out anything because they're not the same type of variable. So all I can do is divide -3, and that's going to leave me with positive 4t to the 4th minus 1z squared. All right. Okay, so then the next example, I don't have a number in front of either of these c's right here. So that tells me that they're really a 1, right? And so the largest number here would just be a 1. Remember, your GCF cannot be bigger than the smallest number value that you have. Now, if we look at the variables, I do have a c here. I have a c on the second term. I have a c in my third term, but there is no c in that last term. It's just a constant. So there's nothing for me to take out other than the 1. So this would be another example that is not factorable. Okay, next example, I have a 3, 15, a 6, and a 30. The smallest value there is a 3, so my GCF cannot be bigger than a 3. All of these numbers are divisible by 3, so that's going to be part of my GCF. Now I look at all my variables. I have an m cubed, an m squared, an m, but my last term does not have any variable on it, so I can't take out a variable. So all I can do is take out a GCF of 3. So 3 divided by 3 is 1, and I'm still left with that m cubed. 15 divided by 3 is 5, and I still have my m squared. 6 divided by 3 is 2, and I still have my m, and 30 divided by 3 is 10. Okay, number 15, I have a 4, a 38, and a 34. So again, looking for the GCF, it can't be bigger than 4 since that's the smallest number that's there. However, 38 and 34 are not divisible by 4, so 4 is not the GCF. So then I would have to think, well, what other numbers can I divide 4 by? And the other number is 2. So does 38 divide by 2? Yes. 34? Yes. They're both even numbers, so I know they're going to divide by 2. Then I look at my variables. I do have an x squared on the first term and an x on the second, but there's no variable on the third, so the only GCF I could take out here is a 2. So when I divide everything by 2, I get 2x squared, 19x, and 17. Okay, and then finally, on this last one, again, like I mentioned in that previous problem, if there's no number there, that's really a 1. So for this one, the largest GCF I can have as far as the number is concerned is 1. But then if I look at my variables, I have an x to the 4th, an x cubed, an x squared, and an x. I do have some version of an x on every single term here, so I can take out that x. So my GCF is just the x, which I'm going to divide out from each term. So x to the 4th divided by x would leave me with x cubed. 2x cubed divided by x would leave me with 2x squared. 16x squared divided by x is going to leave me with minus 16x. And then here the x's cancel, and I just have that 32. Okay, so now let's continue on. So now that you have an idea of how to take those GCFs out, let's go over how to solve some of these polynomial equations where we have to take out that GCF. And then we're going to use something called the zero product property to actually solve the equation and find out what those x values actually equal. Now, of course, these will be our solutions for x, which will also sometimes be referred to as roots because they can be solved using square roots on some occasions, and they will also be referred to as zeros. So all of those terms are synonymous for the solutions in these quadratic equations that we'll be dealing with, or polynomial equations in some cases. They may be other types of polynomials. Okay, so how to use the zero product property. Once your problem is factored out, so maybe you have taken out the GCF out, or as we'll learn later this week, how you could factor a trinomial into two binomials, like this example that we're looking at here. Basically, you have all your x's now singular, and they're all kind of separated into different multiples. So what's going to happen is you have to think to yourself, okay, well, what times something would equal 0? Well, we know that 0 times any number is going to equal 0, right? And we also know any number times 0 equals 0. So if we have an equal 0 here, that means one of these two parentheses would have to equal 0, because once that's 0 and it multiplies to the other one, no matter what it is, it'll equal 0. So in this first example, let's say we have x minus 3 times x plus 6 equals 0. So we're saying, okay, well, if this x minus 3 were equal to 0, then that would make the whole equation equal 0, right? Because if we add 3 here to get x by itself, and we get a 3, for example. If x is 3, 3 minus 3 is 0, and then 0 times whatever's in this parenthesis is going to be 0. It also works this way over here as well. So if you had x minus 3 times x plus 6, and the x plus 6 portion equals 0, and if that were true, x would have to be negative 6. That would also work, because negative 6 plus 6 would equal 0, and 0 times anything in the other parenthesis would give me a 0, and then that would make the equation true. So basically, once you break it up into your smaller factors, each factor just gets set equal to 0, and then you can solve for that one variable. So let's take a look at this first example. So if I already have m minus 7 times m minus 9 equals 0, then that means either my m minus 7 needs to equal 0, or my m minus 9 has to equal 0. Because if one of those parentheses equals 0, then the whole equation would equal 0, and then that would make it true. So in order to solve, what are those values for m that would make that happen? We set it up equal to 0 separately, and then just solve it. So remember, using your inverse operations. So m would equal positive 7, or in this case, if I add 9, m would equal positive 9. So if I put a positive 9 into the equation here, I would have 9 minus 2, 9 minus 7, which is 2. But here I would get a 0. 2 times 0 is 0. It would work. If I put the 7 in, 7 minus 7 would be 0. 0 times negative 2 would still be 0. All right, so let's try the next example. 5n plus 10 equals 0. Or if the second parenthesis, 4n plus 12 equals 0, that would work too. So now to solve these simple equations, you did this way back in chapter 2. You want to get the variable by itself by using your inverse operations. So you're always going to add or subtract that constant to the other side first. So that gives me 5n equals negative 10. And then you want to divide by the number being multiplied to your variable. In this case, it's 5. And that gives me n equals negative 2. On the second half, we're going to move the 12 over by subtracting it. 4n equals negative 12, and then I divide by the 4 to get the n by itself, and I get n equals negative 3. So now in the next example, we're going to use the zero product property to solve them, but first we have to get it in that factored form, and we're going to do that by factoring out the GCF like we worked on the first page. So we're going to write out this original equation. So I have 6x squared plus 12x equals 0. And I need to find that GCF. What is my GCF here? Well, just like we did on that first page, we have a 6 and a 12. What's the smaller of the two? The 6. So we know the GCF can't be bigger than that. Is 12 divisible by 6? Yes. So we know 6 is part of our GCF. So now I'm going to look at my two variables. Again, they're both some version of an x. Whichever one is smaller becomes part of my GCF. So I'm dividing each of these by my GCF of 6x. So now I have the 6x on the outside of the parenthesis. And then when I divide these, 6 divided by 6 is 1. So I'm going to get 1x. And 12 divided by 6 is 2. And those x's cancel. And this is my factored form of that equation. Now I'm going to take each of my factors. So 6x over here is going to equal 0. And then x plus 2 is going to equal 0. And now I can solve and get my two solutions for x. Now in the first one, 6 times x equals 0. So if I divide both sides by 6, I simply get x equals 0 as my first solution. On the other one, I have x plus 2 equals 0, so I'd have to subtract 2 to the other side, and I get x equals negative 2. Okay, so now going on to example 3. So example 3, we're going to do the same thing. We just have to make sure the equation equals 0 before we do anything else, right? So for this one, we want to move that 21y over to the other side. And when we do that, we're going to have to change the sign. So it's going to become 9y squared minus 21y equals 0. Once we get it to equal 0, now we can do the GCF. In this case, my GCF, 9 is the smaller number, so it'd have to be 9 or less, right? But 9 doesn't go into 21. So the other number that does go into 9 is 3, and 3 also goes into 21, so I know my GCF is going to have a 3. Both of these also have y values. The smaller one is just the 3y, so I know that that is my GCF. So now when I divide each of these by that 3y, I'm going to get 3y minus 7. So now I can use both of these using zero product property. 3y equals 0 and 3y minus 7 also equals 0. And now I'm going to solve each one separately and get my two solutions. So on the first half, 3y equals 0. I would want to divide, because that's my inverse operation here. And then I can get y all by itself, and 0 divided by any number is 0. On the second half here, I'm going to have to move my 7 over by adding it. Then I have 3y equals 7, and I'm going to divide. And I end up with y equals 7/3. You can certainly leave it in improper fraction form as long as it's simplified. If you want to change it to a mixed number, 2 1/3, that's fine too. I would refrain from putting it as a repeating decimal though, because that actually wouldn't work if you plugged it back in. Okay, so let's just review a couple more of these. So this one's already set equal to 0, which is nice. So we're going to start out by finding that GCF. This is a 1, so we can't take out any number since there's no number greater than 1 to take out. And they both have a Q. So our GCF here is just going to be that simple Q. And when we divide a Q out from each of these terms, we're left with Q plus 16. So now this first factor, which is just the Q, I'm going to equal to 0. And then there's nothing for me to solve because it's already by itself. On the other side, I'm going to do Q plus 16 equals 0. And all I have to do is subtract the 16, just finish solving for the Q, and I get Q equals negative 16. Okay, on number 4, this time I'm looking for a GCF again. The smaller number is 4, and 8 is divisible by 4, so I know that's part of my GCF. And they both have some version of a K, the smaller one being that single K. So I know 4K is my GCF. Dividing each of these by 4K, I end up with K minus 2. So now I'm going to use my zero product property, setting each of my factors equal to 0, and then solving. So 4 times K is 0. If I divide by 4, I get K equals 0. K minus 2 is 0. I'm going to add 2. K equals 2. All right, in this one here, we have to just move that 36 over because remember, we have to have this equal to 0 in order to solve. Once I've done that, I can now look for a GCF. 12 is the smaller of the two numbers, and 36 divides by 12, so I know part of my GCF will have 12. And then I have an H term, an H value on both of these. The smaller is just the single H, so 12H is my GCF. Now when I divide 12H out here, I'm left with H, and when I divide 12H on the right side, I'm left with 3. So 12H equals 0, and H minus 3 equals 0, and I'm using my zero product property to finish solving for H. So I divide, and I get H equals 0, and over here I'm going to add 3, and I get H equals 3. Now the last thing we're going to do is we're going to apply this in a vertical motion problem. So talking about the height of a projectile, so a projectile would be, let's say, if you shot like a paintball out of a gun, or if you hit a baseball with a bat, or anything like that. So T is representing the time in seconds that the object's in the air. V is the initial velocity in feet per second, and S is the initial height. So where was the object when it was launched? This H will represent the ending height, which is typically the ground, because gravity will pull on that object until it is stopped by something. The negative 16 is the force of gravity on Earth. So here in this example, it says a child jumping rope. So if this is the child, right, and they're jumping rope, they're on the ground when they start, and then obviously they're going to jump up, and then they're going to land on the ground again, right? They're not actually starting at some height or ending at some height except for 0. But the child, they push off or launch themselves at a velocity of 8 feet per second. So the V is going to be 8. So we know the ending height is 0, and we know the H will also be 0, because, or the starting height is 0 and the ending height is also 0. So if we were going to use this model, initially we're just going to have H equals negative 16t squared plus 8t plus that starting height, which was 0, because they're starting on the ground. Now, in order to do anything with this problem, we would need to make this H be a 0. So I'll do that. Right, now, because the starting height was 0 here, we don't need to include that anymore. We don't have to write plus 0. And now we're going to put that 0 in for the H, since we know they're going to end at the ground as well. They're not jumping up onto something, they're jumping back down to the same level they started. So now that this is equal to 0, we can use the same method we've been doing to solve this. So what is the GCF here? Well, remember, it can't be bigger than the smaller number, which is 8. Because my lead coefficient is a negative, I want to factor that out. And then they both have a t, and the smaller t is that single t. So I'm taking out a negative 8t, and then I'm going to be left with positive 2t minus 1. And of course, that all equals 0. So now I'm going to take each of my factors and use that zero product property. So negative 8t equals 0, 2t minus 1 equals 0, and I'm going to solve these. And when I solve the first one, I get t equals 0, which doesn't make very much sense. You can't be jumping in the air for 0 seconds. And then the other one, I'm going to add 1 and divide, and I get t equals 1/2, or half a second. So that is the only answer that makes sense. So typically when you do these kind of problems, you'll get one answer that's a throwaway or it doesn't make sense, and the other answer will be the correct answer. So let's just do one more. So in this case, let's suppose that velocity was 10 feet per second. So H equals negative 16t squared plus 10t. Again, we're going to replace that H with a 0, because again, it's the same situation. The child is still jumping up and then landing back on the ground. This time, however, my GCF, 10 is the smaller number, but 10 does not go into 16, so that's not the GCF. So 5 does not go into 16, so then I'm thinking of 2. So 2 is the greatest common factor here. Now I'm going to put a negative on my 2 because my lead coefficient is negative. And both of these have a variable with a t, and the smaller one is just that single t. So if I divide out my negative 2t, I'm left with positive 8t minus 5, and of course, that equals 0. So now I can use my zero product property to solve for these two answers. Negative 2t equals 0. 8t minus 5 equals 0. On this side, I'm going to divide and get the t, which is 0. On this side, I'm going to add 5 and then divide by 8, which gives me t equals 5/8. So since I'm finding how long this child was in the air for, 0 seconds doesn't make sense, but 5/8 seconds would make sense.